The concept of cosmic inflation is a fascinating idea in cosmology, proposing that the universe underwent an incredibly rapid expansion just after the Big Bang, which occurred around 13.8 billion years ago. This theory, introduced in the 1980s by physicist Alan Guth, suggests that during this brief period, the universe expanded at a rate much faster than the speed of light, smoothing out any irregularities and leading to the uniformity we observe in the cosmic microwave. As scientists studied the cosmic microwave background, or CMB, they found that it is remarkably homogeneous, with tiny fluctuations that reflect the density variations in the early universe, supporting the inflationary model. One of the most compelling pieces of evidence for cosmic inflation comes from the observations made by the Planck satellite, which measured the CMB's temperature fluctuations with great precision. The data revealed a flat universe consistent with inflation, and these fluctuations provided insights into the initial conditions of the universe, suggesting that inflation not only explains the uniformity, but also the large-scale structure we see today. Moreover, the theory of inflation predicts the existence of gravitational waves, ripples in space-time caused by the rapid expansion, which could potentially be detected by experiments like LIGO or future missions aimed at measuring the polarization of the CMB. As researchers delve deeper into the implications of inflation, they consider how it might explain the distribution of galaxies and the cosmic web, the large-scale structure of the universe. The inflationary model posits that quantum fluctuations during this rapid expansion led to regions of varying density, which would later evolve into galaxies and clusters of galaxies. The alignment of the CMB's fluctuations with the distribution of galaxies in the universe provides further support for inflation, as it suggests a direct correlation between the early universe's conditions and the current structure of the cosmos. Additionally, cosmic inflation offers solutions to several puzzles in cosmology, such as the flatness problem, which questions why the universe appears so flat on large scales, and the horizon problem, which addresses why regions of the universe that are far apart have the same temperature, not being able to influence each other. Inflation postulates that these regions were once close together before the rapid expansion carried them apart, providing a coherent explanation for these observations. Critics of cosmic inflation argue that it introduces new problems, such as the need for a detailed mechanism to trigger inflation and to stop it, leading to ongoing. Some alternative theories have been the theory of cosmic inflation suggests that just after the Big Bang, the universe underwent a rapid expansion, much faster than the speed of light, which is quite mind-boggling when you think about it. This expansion occurred in a fraction of a second, specifically during the first 36 to 32 seconds after the universe began. And during this incredibly brief period, the universe expanded exponentially, growing from. This theory was proposed in the 1980s by physicist Alan Guth, and it was developed further by other scientists, like André Linde and Paul Steinhardt, who contributed to the understanding of how inflation could solve various problems in cosmology. One of the key aspects of inflation is that it addresses the horizon problem, which questions why distant parts of the universe that have never been in contact with each other exhibit such uniform temperature and density. Because of inflation, regions that are now far apart were once close together, allowing them to equilibrate before they were pushed apart by the rapid expansion. Another intriguing point is the flatness problem, which refers to the observed geometry of the universe being very close to flat, which is another thing that inflation helps to explain. By stretching the fabric of space, inflation makes the universe appear more uniform and flat, much like how a balloon, when inflated, appears smooth and round. Moreover, inflation might also provide a mechanism for the formation of large-scale structures in the universe. During the rapid expansion, tiny quantum fluctuations could have been stretched out, leading to the distribution of galaxies and galaxy clusters we observe today. These fluctuations are thought to be the seeds from which galaxies formed, as they created regions of slightly different densities that eventually led to gravitational attraction and the formation of stars and galaxies. Inflation also has implications for the early conditions of the universe, suggesting that it was not only incredibly hot and dense, but also that it experienced a phase of extremely rapid cooling, which allowed for the formation of fundamental particles and forces. The theory of cosmic inflation is supported by various observations, including the cosmic microwave background radiation, which shows slight fluctuations that align well with the predictions made by inflationary models. These observations lend credence to the idea that inflation was a critical phase in the evolution of the universe, although there is still much research being conducted to deepen our understanding of this fascinating concept. The concept of cosmic inflation, which suggests that the universe underwent a rapid expansion in its earliest moments, was first proposed by the physicist Alan Guth in 1980. This groundbreaking idea emerged from the desire to solve certain puzzles in cosmology, particularly the uniformity of the cosmic microwave background radiation and the flatness problem of the universe. Guth's theory posited that, just after the Big Bang, the universe expanded exponentially in size, increasing by a factor of at least 10^26, then a tiny fraction of a second. This inflationary phase would have smoothed out any irregularities, leading to the homogeneous and isotropic universe we observe today. Importantly, Guth's initial model of inflation was later refined and expanded upon by other physicists, including André Linde and Paul Steinhardt, who contributed additional insights and variations to the theory, ensuring that it became a cornerstone of modern cosmological understanding. The implications of this theory have been profound, influencing not only our understanding of the early universe, but also the formation of large-scale structures within it, and providing a framework that has been supported by various observations, such as the detailed measurements of the cosmic microwave background by missions like the Wilkinson Microwave Anisotropy Probe and the Planck Satellite. This idea of cosmic inflation has opened up new avenues of research and has enriched the discussion around the origins of the universe, while also raising further questions about the nature of the cosmos. The possibility of multiple universes and what might lie beyond the observable universe. Cosmic inflation, a theory that has reshaped our understanding of the universe's early moments, was primarily developed to address several significant puzzles that arose from the standard Big Bang model. One of the main motivations was the horizon problem, which questions why distant regions of the universe, seemingly isolated from one another, exhibit similar temperatures and properties. If the universe expanded uniformly after the Big Bang, then these regions should not have been able to exchange information or energy, leading to differing temperatures. Yet observations show they are remarkably homogeneous. Inflation proposes that a rapid expansion occurred in the universe's infancy, stretching these regions beyond each other's causal horizons, thus explaining their uniformity. Another driving factor behind the development of inflationary theory is the flatness problem. Observations indicate that the universe is remarkably flat, which means that its geometry is very close to that of Euclidean space. In the standard Big Bang model, any slight deviation from flatness would have grown over time, leading to a universe that is either open. However, inflation suggests that the early rapid expansion would have driven the universe towards flatness, smoothing out any irregularities and making the universe appear flat at large scales. Additionally, the existence of primordial density fluctuations is another motivation for inflation. According to quantum mechanics, tiny fluctuations in the energy density of the universe could have occurred during the inflationary period. These fluctuations would eventually seed the large-scale structure we observe today, such as galaxies and galaxy clusters. Inflation provides a natural mechanism for generating these fluctuations, linking the microscopic quantum realm to the macroscopic structure of the universe. Another aspect that fuels interest in inflation is its compatibility with observations of the cosmic microwave background radiation, which is the afterglow of the Big Bang. Measurements from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have shown patterns in the temperature fluctuations of the Keem B that align closely with predictions made by inflationary models. This connection between theory and observation has strengthened the case for inflation as a crucial phase in the universe's evolution. Moreover, the potential for inflation to explain the observed large-scale structure of the universe is a significant motivation. The theory offers a compelling framework for understanding how small quantum fluctuations could grow into the vast cosmic web of galaxies and voids we see today. This evolution from quantum fluctuations to the structure of the universe involves complex processes, yet inflation provides a clear pathway, making it an attractive concept for astronomers and cosmologists alike. In addition to these scientific motivations, The cosmic inflation is a fascinating concept that helps explain some of the most puzzling features of our universe, particularly the uniformity of the cosmic microwave background, or COOM, which is the faint afterglow of the Big Bang. The COOM is remarkably uniform, with tiny fluctuations, but overall, it looks almost the same in every direction we look, which raises the question of how such uniformity can exist across vast distances, especially when those regions of space have not had time to interact with one another. Big Bang. Cosmic inflation addresses this by proposing a period of rapid expansion in the very early universe, occurring just fractions of a second after the Big Bang. During this brief moment, the universe expanded, exponentially stretching the fabric of space itself. Imagine blowing up a balloon. As you blow, the surface of the balloon expands, and points on that surface become farther apart. This inflationary phase would have taken tiny quantum fluctuations that existed at a very small scale and stretched them across the universe, creating a uniform background that would later cool and evolve into the COOM. As the universe inflated, regions that were once very close together became widely separated, and this rapid expansion ensured that the observable universe became homogeneous and isotropic, meaning it looks the same in all directions. This uniformity is crucial because without inflation, the regions of space that we now observe as having a similar temperature and density would not have been in causal contact with each other, as they would be too far apart for light to travel between them in the time since the Big Bang. This leads to what is known as the horizon problem, which inflation neatly solves. The inflationary model suggests that the early universe was in a hot and dense state before the rapid expansion, allowing for the uniform temperature we observe in the COOM, despite the vast distances that separate various parts of the universe. The tiny fluctuations in the COOM reflect the initial conditions of the universe, and these were amplified and spread out by inflation around us, from galaxies to stars. And even our own planet, quantum fluctuations play a crucial role in inflationary theory, which describes the rapid expansion to have occurred just after the Big Bang. In simple terms, quantum fluctuations refer to the temporary changes in energy that occur in empty space, as predicted by quantum mechanics. These fluctuations are not just random. They are fundamental to the fabric of the universe. During the inflationary period, which lasted a tiny fraction of a second, these fluctuations in energy density were magnified by the extreme expansion of space. As the universe expanded exponentially, tiny quantum fluctuations were stretched across vast distances, leading to variations in density throughout the cosmos. These variations, which might have been on the scale of just a tiny fraction of a proton, eventually became the seeds for the large-scale structure of the universe, influencing where galaxies and clusters would form. In essence, inflationary theory suggests that the very small quantum-scale fluctuations provided the initial conditions necessary for the universe's large-scale structure we observe today. Research in this area often focuses on the implications of these fluctuations for the cosmic microwave background radiation, which is the afterglow of the Big Bang and provides a snapshot of the universe when it was just about 380,000 years old. Scientists have found that the slight temperature variations in the cosmic microwave background align remarkably well with the predictions made by inflationary theory. Furthermore, experiments, such as those conducted by the Planck satellite, have provided detailed maps of the cosmic microwave background, allowing researchers to analyze the density fluctuations that arose from these quantum fluctuations. The consistency of these observations with inflationary models supports the idea that quantum fluctuations were indeed instrumental in shaping the cosmos. Additionally, the specific mechanisms of how these fluctuations influence the universe are still being explored, with various models proposing different ways in which they can lead to the formation of structures. Some theorists suggest that scalar fields, which are hypothetical fields that permeate space, could be responsible for driving inflation and managing these quantum fluctuations. As scientists continue to probe deeper into the nature of dark energy and the fate of the universe, understanding the role of quantum fluctuations in inflationary theory remains a vital area of research, as it bridges the gap between quantum mechanics and cosmology, revealing the connections between the smallest scales of reality and the vastness of the cosmos. Cosmic inflation is a fascinating concept in cosmology that offers a unique solution to what is known as the horizon problem, which arises when we consider the uniformity of the cosmic microwave background radiation, or KEEM, observed throughout the universe. The horizon problem stems from the fact that regions of space, which are extremely far apart from each other, seem to have the same temperature and similar physical properties, despite the fact that, according to the standard Big Bang model, they have never been in contact with one another, given that light from one region would not have had enough time to reach the other before the universe expanded too rapidly. This uniformity appears puzzling, leading scientists to wonder how these distant regions could have come to such similar states, especially since they should not have had the chance to interact or exchange information. Cosmic inflation, which proposes a brief period of exponential expansion of the universe in the very first moments after the Big Bang, offers a compelling answer to this dilemma. According to this theory, during inflation, the universe expanded at an astonishing rate, stretching space itself. This rapid expansion would have allowed regions that are now far apart to have once been very close together, essentially within each other's causal horizon, meaning they could interact and come to thermal equilibrium before inflation stretched them across vast distances. As a result, the uniform temperature of the COOM can be explained, as all these regions would have shared the same conditions before inflation took hold, essentially smoothing out any variations. Moreover, the inflationary model predicts that tiny quantum fluctuations in energy density which occurred during inflation would be stretched to cosmic scales, leading to the large-scale structure we observe today, such as galaxies and clusters of galaxies. These fluctuations provide the seeds for the formation of structures in the universe, giving us insights into how the cosmos evolved after inflation ended and regular expansion took over. The successful predictions made by the inflationary model, along with the observations of the calm by missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, lend strong support to the idea of inflation, indicating that it not only addresses the horizon problem, aligns with a broader understanding of cosmic evolution. In summary, cosmic inflation resolves the horizon problem by suggesting that regions of the universe that appear synchronous today were once in close proximity, allowing them to equilibrate before being stretched apart, thus explaining the uniformity of the growth of cosmic structure. Making inflation a cornerstone of modern the flatness problem is a fascinating concept in cosmology that addresses a significant question about the shape of the universe. When scientists look at the universe, they observe that it appears to be very close to flat, meaning that the geometry of space is not curved on large scales. This observation raises an important issue, because if the universe were to follow the predictions of standard Big Bang cosmology, it should contain either a positive curvature, like a sphere, or a negative curvature, like a saddle. Instead, measurements, particularly from the cosmic microwave background radiation, suggests that the universe is remarkably flat to an astonishing degree. The flatness problem arises because, according to cosmological models, the density of matter and energy in the universe must be very close to a critical value for the universe to remain flat. If the density were even slightly different in the early universe, the universe would have quickly evolved into a state that was either open or closed, rather than flat. This leads to a perplexing question. Why is the universe so flat today, given these conditions? How did it avoid falling into one of these other geometries, which would have been expected based on its initial conditions? This is where the theory of cosmic inflation comes into play. Inflation posits that, in the very early moments after the Big Bang, the universe underwent a rapid exponential expansion, expanding faster than the speed of light for a brief period. This inflationary phase stretched out any initial curvature, smoothing out the geometry of space, much like how a balloon expands and becomes more uniform as you blow it up. Because of this rapid expansion, any tiny irregularities in the density of matter were stretched out over vast distances, effectively diluting them. When the inflationary phase ended, the universe cooled and the standard Big Bang expansion took over. At this point, the universe had expanded so much that any curvature present was drastically reduced, resulting in a universe that appears flat on cosmic scales. Thus, inflation provides a compelling resolution to the flatness problem by explaining how the universe could evolve from potentially curved initial conditions to the remarkably flat universe we observe today. The elegance of this theory lies in its ability to align with observational data, such as the uniformity of the cosmic microwave background and the distribution of galaxies, making it a cornerstone of modern cosmological understanding. The concept of inflation plays a crucial role in our understanding of the early universe, particularly in the context of inflationary models, which propose that the universe underwent an exponential expansion in its very first moments. This idea, first suggested in the 1980s by cosmologist Alan Guth, addresses several puzzles in cosmology, such as the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe we observe today. The inflaton is a hypothetical particle that is believed to have driven this rapid expansion, and its properties are essential to the mechanics of inflation. According to inflationary theory, right after the Big Bang, the universe was in a hot, dense state, teeming with energy. This energy is thought to have been associated with the inflaton field, a scalar field that can take on various values throughout space and time. As this field evolved, it increased in energy density, which led to a repulsive gravitational effect, causing the universe to expand at an accelerating rate. One of the fascinating aspects of the inflaton is that it is not a particle we have directly observed. Rather, it is a theoretical construct that helps explain the dynamics of the early universe. The significance of the inflaton lies not only in its role in driving inflation, but also in its implications for the universe's structure and the distribution of galaxies. As the universe expanded, quantum fluctuations in the inflaton field became stretched over vast distances, eventually leading to the formation of density fluctuations. These fluctuations are thought to be the seeds of the large-scale structures we see today, like galaxies and clusters of galaxies. Therefore, understanding the inflaton and its properties is not just about explaining the rapid growth of the universe, but also about connecting the early universe's conditions to the observable structures we see in the cosmos. Additionally, various models of inflation propose different types of inflatons, each with unique characteristics and implications for the universe's fate. Some models suggest that the inflaton could be a simple, single scalar field, while others propose more complex scenarios involving multiple fields or non-standard interactions. These distinctions can lead to different predictions about the universe's geometry, the nature of dark energy, and the ultimate fate of cosmic expansion. In summary, the inflaton is a foundational concept in modern cosmology and helps to bridge the gap between the conditions of the early universe and the structure we observe in the present day. The study of the inflaton continues to be a vibrant area of research. The inflationary period is a fascinating concept within the broader timeline of the Big Bang theory, and it plays a crucial role in our understanding of the early universe. To grasp its significance, we first need to consider the timeline of events that unfolded after the Big Bang, which is estimated to have occurred around 13.8 billion years ago. The Big Bang itself marks the moment when the universe began to expand from an extremely hot and dense state. But what happened in the first moments after this event is still a subject of active research and discovery. According to the traditional Big Bang theory, The universe began to cool rapidly as it expanded, and within the first few minutes, protons and neutrons formed, leading to the creation of light elements like hydrogen and helium through a process known as Big Bang nucleosynthesis. However, the inflationary period, which is thought to have occurred just a fraction of a second after the Big Bang, adds an important layer to this narrative. During this brief yet pivotal moment, the universe is believed to have undergone an exponential expansion, growing from subatomic scales to about the size of a grapefruit in an incredibly short time frame, approximately 10/13 after the Big Bang. This rapid expansion, known as cosmic inflation, is thought to have been driven by a field called the inflaton field, which caused space itself to stretch. This means that while matter was still in its infancy, the fabric of space expanded faster than the speed of light, smoothing out any irregularities and leading to a uniform distribution of energy. The inflationary period helps to explain several puzzles that arise from the standard Big Bang model, such as the observed uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. Without inflation, it would be challenging to understand why distant regions of space, which have never been in contact with each other, appear so similar in temperature and density. Moreover, inflation sets the stage for the formation of galaxies and cosmic structures. As the universe cooled after inflation ended, tiny quantum fluctuations in the inflaton field were stretched across the universe, leaving behind slight variations in density. These variations became the seeds for the gravitational attraction that eventually formed galaxies, stars, and other structures we see today. So, while the Big Bang theory provides the framework for the universe's origin, the inflationary period enriches our understanding of how that universe evolved from a hot, nearly homogeneous state into the complex structure we observe now. The inflationary epoch in the universe's history, which occurred just after the Big Bang, is characterized by a rapid and exponential of space, a phenomenon that is both fascinating and complex. This period, lasting only a fraction of a second, is believed to have taken place roughly between 10:36 seconds and 10:32 seconds after the Big Bang, during which the universe expanded fast. This swift expansion smoothed out any initial irregularities, leading to a uniform distribution of energy and matter throughout the cosmos. And it is thought to have stretched tiny quantum fluctuations into the seeds of all the structures we see in the universe today. Galaxies. One of the key features of this epoch is the idea that it was driven by a field known as the inflaton field, which is a hypothetical scalar field responsible for this rapid expansion. As the inflaton field decayed, it released energy that contributed to the heat and density of the universe, transitioning it from the inflationary phase to the hot, dense state that characterizes the early universe. This process not only explains the uniformity of the cosmic microwave background radiation, but also links to the formation of large-scale structures in the universe. Another important characteristic is the concept of horizon problem, which refers to the observation that regions of the universe that are far apart from each other seem to have the same temperature and properties, even though they should not have been in contact with one another since they were outside each other's causal influence. Inflation provides a solution to this issue by suggesting that these regions were once much closer together and then expanded rapidly, allowing them to equilibrate in temperature before being pushed far apart. Additionally, during this epoch, the universe underwent a phase transition, which is similar to how water turns to ice as the inflaton field settled into a lower energy state. This transition released energy and resulted in the creation of particles, leading to the hot, dense plasma that eventually cooled and formed atoms, stars and galaxies. Moreover, the inflationary epoch explains the current large-scale structure out quantum fluctuations, which later evolved into the density variations that led to galaxy formation. The predictions made by inflationary models have been supported by observations of the cosmic microwave background radiation, particularly measurements from satellites like the Planck spacecraft, which have provided strong evidence for this theory. In summary, the inflationary epoch represents a critical moment. Inflationary models in cosmology aim to explain the rapid expansion of the universe that occurred shortly after the Big Bang, and different models like chaotic inflation and new inflations for this early period. Chaotic inflation, introduced by Alexei Starobinsky and later expanded upon by André Linde, suggests that inflation can occur in a vast number of regions, each governed by different fields and conditions, leading to chaotic inflation. The idea is that the universe can undergo inflation even if it starts from a high energy state, where random fluctuations can trigger inflation in certain parts of space, allowing them to expand exponentially. This model allows for a variety of different outcomes, depending on the initial conditions and the potential energy landscape of the scalar field driving inflation, which means that different regions of the universe could evolve into different types of universes, each with its own physical laws. On the other hand, new inflation, developed by Alan Guth, is characterized by a more structured approach. This model suggests that inflation happens in a more homogeneous and isotropic universe, where the scalar field slowly rolls down a potential, causing a gradual increase in the size of the universe. This rolling motion leads to a smooth inflationary phase that can last for a substantial period, eventually transitioning to a hot Big Bang. In new inflation, the initial conditions are more finely tuned to ensure that inflation can occur and that it ends in a uniform, smooth manner, which allows for the generation of the density fluctuations that ultimately lead to the large-scale structure we observe today. While both chaotic and new inflationary models successfully address the flatness and horizon problems of cosmology, they differ in how they conceptualize the process of inflation itself. Chaotic inflation provides a broader framework that accommodates a multitude of possible outcomes, and the existence of many separate regions, or universes. Whereas new inflation focuses on a singular, more ordered inflationary phase that leads directly to the observable universe we inhabit. In terms of their predictions, chaotic inflation can lead to a vast landscape of possible physical realities, which means that it raises interesting questions about the nature of reality and the potential for other universes with different properties. New inflation, however, emphasizes a more coherent narrative of our universe's early moments, ensuring that the conditions leading to the Big Bang are less random and more a result of specific dynamics within the scalar field. Both models have their strengths and weaknesses and ongoing observations, such as those from the concept of cosmic inflation, which proposes that the universe underwent an exponential expansion in its earliest moments, has gathered substantial observational support over the years. One of the most significant pieces of evidence comes from the cosmic microwave background radiation, or COOM, which is the afterglow of the Big Bang. When scientists analyze the temperature fluctuations in the COOM, they find that these tiny variations are consistent with predictions made by inflationary models. The uniformity of the come across the sky suggests that, at some point, the universe was incredibly uniform, but the small irregularities we observe today may have originated from quantum fluctuations during the inflationary period, which were stretched across the universe as it expanded. Moreover, the large-scale structure of the universe provides further support for cosmic inflation. Observations of galaxies and galaxy clusters reveal that they are not randomly distributed, but rather they follow a pattern that aligns with the density fluctuations predicted by inflationary theories. This large-scale structure, including the web-like formation of galaxies, supports the idea that these fluctuations were seeded during the rapid expansion of the early universe. Another vital piece of evidence arises from gravitational waves, which are ripples in space-time caused by massive accelerating objects. If inflation occurred, it would have generated a specific pattern of gravitational waves. Scientists are currently working to detect these waves, and experiments like LIGO and future observatories are designed to observe these minute signals. While direct detection remains elusive, the potential discovery of these primordial gravitational waves would provide a powerful confirmation of inflation. Additionally, the abundance of light elements such as helium, deuterium, and lithium observed in the universe today aligns with predictions made by Big Bang nucleosynthesis, which is consistent with inflationary models. The processes that occurred during inflation could have influenced the distribution and formation of these elements, further validating the concept. Lastly, the observations made by the Planck satellite, which mapped the COOM with extraordinary precision, have provided critical data that supports inflation. The measurements of the COOM's temperature and polarization have been analyzed to yield a detailed picture of the early universe, and the findings match closely with inflationary predictions. This comprehensive dataset enhances our understanding of cosmic inflation and strengthens the argument for its role in shaping the universe as we see it today. Each of these pieces of evidence, when considered together, paints a compelling picture of a universe that expanded rapidly, setting the stage for the cosmos we inhabit now. Primordial gravitational waves are ripples in space-time that are thought to have been produced during the very early moments of the universe, particularly during an event known as cosmic inflation, which occurred just after the Big Bang, around 10 to the minus 32 seconds after the universe began. During this incredibly brief period, the universe underwent an exponential expansion, stretching space itself, and this rapid growth is believed to have generated gravitational waves, which are fluctuations in the gravitational field. These waves, although incredibly faint, carry with them important information about the conditions of the early universe, providing a unique window into the events that shaped the cosmos. In inflationary theory, these gravitational waves are significant because they are predicted to be a key signature of the inflationary process. As the universe expanded at such a fast rate, quantum fluctuations, tiny variations in energy, were stretched to cosmic scales, leading to the creation of gravitational waves. The presence of these primordial waves can influence the cosmic microwave background radiation, which is the afterglow of the Big Bang, by creating specific patterns in the polarization of this radiation. Scientists are working diligently to detect these waves, as finding them would provide strong evidence supporting inflationary theory. Efforts like those conducted by observatories such as LIGO and upcoming missions like the space-based observatory LISA aim to measure these waves indirectly by observing their effects on the cosmic microwave background. The discovery of primordial gravitational waves would not only validate the inflationary model, but also enhance our understanding of the fundamental physics of the early universe, potentially shedding light on the nature of dark energy and the forces that govern cosmic evolution. The quest to understand these waves is not merely about confirming theories. It's about exploring the very fabric of reality, as it could lead to new insights into the origins of the universe itself, and the underlying mechanisms that drive its expansion. The cosmic microwave background radiation, often referred to as COOM, is a relic of the early universe, and it plays a crucial role in our understanding of cosmology, particularly in providing evidence for the theory of inflation. To grasp this, it's essential to know that the COOM is the afterglow of the Big Bang, a faint, uniform radiation that fills the universe, and it was first detected in 1965 by Arno Penzias and Robert Wilson, leading to a Nobel Prize in Physics for their discovery. When we look at the COOM today, it appears as a nearly uniform glow with slight temperature fluctuations that correspond to density variations in the early universe. These variations are incredibly small, only about 1 part in 100,000, but they carry significant information. Inflation theory, proposed by Alan Guth in the 1980s, suggests that the universe underwent a rapid exponential expansion in its first moments after the Big Bang, lasting only a fraction of a second. This theory helps explain several perplexing observations about the universe, such as its large-scale uniformity and the distribution of galaxies. The comb serves as a snapshot of the universe when it was just about 380,000 years old, a time when protons and electrons combined to form neutral hydrogen atoms, allowing photons to travel freely through space for the first time. The temperature fluctuations in the comb, which are caused by quantum fluctuations in the density of matter during the inflationary period, can be analyzed today through detailed measurements, particularly by missions like the Wilkinson Microwave Anisotropy Probe, or WUMAP, and the Planck satellite. These measurements have shown that fluctuations follow a specific statistical pattern predicted by inflationary models. This pattern, known as the power spectrum, indicates that the universe is flat and that the density of matter and energy is very close to the critical density needed to keep the universe from collapsing or expanding indefinitely. Moreover, inflation predicts that regions of the universe that are now far apart were once in close contact, meaning they could exchange energy and information. The uniformity of the comb across vast distances supports this idea, as it suggests that the universe was very homogeneous in its early stages. If inflation had not occurred, we would expect to see much larger variations in temperature across the comb, due to the different regions being unable to communicate before the universe expanded so rapidly. Furthermore, the comb also exhibits what are known as acoustic peaks, which are related to sound. The cosmic microwave background, or COMB, is a crucial relic from the early universe, providing us with a snapshot of the cosmos when it was just about 380,000. One of the most fascinating aspects of the COMB is its temperature anisotropies, which are tiny fluctuations in temperature across the sky. These anisotropies, while subtle, often just a few microkelvins, hold immense significance in our understanding of the universe, particularly in relation to the theory of inflation. Inflation theory posits that the universe underwent a rapid exponential expansion just after the Big Bang, smoothing out the initial irregularities in density while also creating quantum fluctuations. These fluctuations eventually grew into the large-scale structures we observe today, such as galaxies and galaxy clusters. The COMB's temperature anisotropies are direct evidence of these quantum fluctuations, as they represent the seeds of cosmic structure. The patterns and distributions of these anisotropies provide clues about the physics of inflation, including the nature of the inflaton field, which is theorized to drive this rapid expansion. The significance of the COMB's temperature anisotropies also lies in how they relate to the density fluctuations in the universe. By measuring the specific characteristics of these anisotropies, scientists can infer the density and composition of the universe, leading to insights about dark matter, dark energy, and the overall geometry of the cosmos. The angular scale of these fluctuations is particularly important. For example, is influenced by the rate of inflation. These data sets have provided a wealth of information that has allowed cosmologists to refine their models of inflation. For instance, the statistical properties of the anisotropies, such as their power spectrum, help in testing various inflationary models, revealing whether they align with observations or need modifications. Moreover, the temperature fluctuations are not only a window into the past, but also a tool for understanding the universe's fate. The way these anisotropies evolve over time can indicate how structures will grow and change, which ties back into the questions surrounding dark energy and the ultimate fate of cosmic expansion. In summary, the significance of the Coombs temperature anisotropies in relation to inflation cannot be overstated, as they provide the Planck satellite, launched by the European Space Agency in 2009, has significantly advanced our understanding of the universe, particularly in the realm of inflation, which is the theory that proposes a rapid expansion of space in the early moments after the Big Bang. By measuring the cosmic microwave background radiation, or CORM, which is the afterglow of the Big Bang, Planck has provided a wealth of data that helps us piece together the conditions of the early universe. The satellite's high-resolution maps of the CORM have enabled scientists to study temperature fluctuations across the sky, revealing tiny variations, or anisotropies, that carry important information about the universe's infancy. One of the key contributions of the Planck satellite is its precise measurements of these temperature fluctuations, which are believed to be the seeds of all current structures in the universe, such as galaxies and galaxy clusters. Planck's data has allowed researchers to refine their models of inflation, offering insights into the rate of expansion and the energy scale at which inflation occurred. This is important because it helps scientists understand not just how inflation happened, but also what might have driven it, including potential candidates for the inflationary field, such as the hypothetical inflaton particle. Moreover, Planck's observations have provided strong evidence for the inflationary model by confirming the predictions made by inflationary theory regarding the statistical properties of the CORM fluctuations. For instance, the satellite's data has shown that the fluctuations are nearly Gaussian, which aligns with the predictions of many inflationary models, suggesting that the initial density perturbations were caused by quantum fluctuations during inflation. This supports the notion that inflation was a rapid, exponential expansion, smoothing out the universe and leading to its large-scale uniformity. Additionally, Planck's measurements have allowed scientists to determine the curvature of the universe with remarkable accuracy, indicating that the universe is flat with only a slight margin of error. This flatness is a critical feature of inflationary theory, as it suggests that the universe underwent a rapid expansion, flattening out any initial curvature. The satellite's results have also helped refine key cosmological parameters, such as the Hubble constant and the density of dark matter and dark energy, further enhancing our understanding of the universe's composition and evolution. In summary, the observations made by the Planck satellite have not only substantiated the theory of inflation, but have also provided a clearer picture of the fundamental processes that shaped the early universe. Offering a deeper understanding of the cosmos and its origins, the BICEP-2 results, announced in 2014, marked a significant moment in the field of cosmology, particularly regarding our understanding of inflationary theory. Inflation, a period of rapid expansion in the early universe, helps to explain several observed features of the cosmos, including the uniformity of the cosmic microwave background radiation, or CMB, and the large-scale structure of the universe. The BICEP-2 team claimed to have detected gravitational waves in the CMB, which they interpreted as evidence of inflation occurring in the very early moments after the Big Bang. This was seen as a potential breakthrough, as it suggested that inflation could produce a unique signature in the polarization of the CMB, specifically the presence of B-mode polarization patterns. If these results were confirmed, they would support the idea that inflation not only occurred, but also provide insights into the physics of the very early universe. However, the implications of the BICEP-2 plex, if the gravitational waves detected were indeed a result of inflation, it could potentially provide a window into understanding the energy scale of inflation, helping scientists to probe the physics of the universe at energies that are otherwise inaccessible. This would allow researchers to explore models of inflation and perhaps narrow down the many competing theories that aim to explain how and why inflation occurred. Yet, the excitement was tempered by subsequent analyses which indicated that the BICEP-2 results might have been contaminated by foreground dust in our galaxy, complicating the interpretation of the findings. This brought about a crucial conversation in the cosmological community regarding the need for more precise measurements and observations. The implications of the BICEP-2 findings pushed researchers to pursue more advanced observational techniques and instruments, such as the Planck satellite, which provided more detailed maps of the CMB, allowing for a better understanding of the polarization patterns and the potential contamination from interstellar dust. This ongoing dialogue emphasizes the importance of collaboration and verification in science, as theories must be rigorously tested against new data and the possibility of alternate explanations. The BICEP-2 results have also sparked discussions around the potential for future experiments which aim to detect B-mode polarization with even greater sensitivity, helping to solidify or refute the claims made by the BICEP-2 team. The quest to understand inflation and its implications for the fundamental nature of the universe continues to be an exciting area of research, reshaping our understanding of cosmology and the evolution of the universe. The interplay between theory and observation remains the concept of cosmic inflation is a fascinating aspect of modern cosmology, and it plays a crucial role in understanding the large-scale structure of the universe. According to the theory of cosmic inflation, which was proposed by physicist Alan Guth in the early 1980s, the universe underwent a rapid expansion, much faster than the speed of light, during its very early moments, specifically within a fraction of a second after the Big Bang. This inflationary period caused the universe to grow exponentially, smoothing out any irregularities and leading to a more uniform distribution of matter and energy. As a result, the large-scale structure we observe today, including galaxies, clusters of galaxies, and vast cosmic voids, can be traced back to those initial fluctuations that were stretched and amplified during inflation. These fluctuations, often referred to as quantum fluctuations, originated at a subatomic level and were imprinted on the fabric of space-time. When inflation occurred, these tiny variations in density were stretched across the cosmos, becoming the seeds from which all the large-scale structures emerged. The inflationary model suggests that regions of slightly higher density would eventually gravitationally attract more matter, leading to the formation of galaxies and galaxies and galaxies and galaxy clusters, while regions of lower density would become vast, empty spaces or voids. This process is supported by observations of the cosmic microwave background radiation, which is the afterglow of the Big Bang, and shows slight temperature fluctuations that mirror the density variations predicted by inflation. Furthermore, the influence of cosmic inflation extends beyond mere structure formation. It also helps to solve several puzzles in cosmology, such as the horizon problem and the flatness problem. The horizon problem arises because regions of the universe that are now widely separated appear to have the same temperature, even though they could not have exchanged information due to the finite speed of light. Inflation explains this by suggesting that these regions were once close together before being pushed apart by rapid expansion. The flatness problem refers to the question of why the universe appears to be so geometrically flat. Inflation predicts that the universe would have been extremely flat before inflation began, which has persisted since then. In summary, cosmic inflation is integral to our understanding of the large-scale structure of the universe, as it not only accounts for the uniformity and isotropy we observe today, but also provides a framework for understanding the formation of structure from quantum fluctuations. The interplay between inflation and gravity has profound implications for cosmology, linking the smallest scales of quantum physics with the vastness of cosmic in the realm of cosmology. The concept of the inflationary bubble plays a crucial role in understanding the early universe, particularly in the context of the Big Bang theory. The significance of the inflationary bubble lies in its ability to explain how the universe transformed from a hot, dense state into the vast, cooler cosmos we observe today. According to the theory, shortly after the Big Bang, the universe underwent a rapid expansion, stretching exponentially in size over a tiny fraction of a second. This dramatic increase in volume, which is what we refer to as inflation, helped to smooth out the distribution of matter and energy throughout the universe, creating a uniform cosmic background. This inflationary period is thought to have been driven by a mysterious form of energy, often called inflaton, which caused space itself to expand at an incredible rate. The significance of the inflationary bubble can also be seen in how it addresses several outstanding questions in cosmology, such as the flatness problem, which asks why the universe appears so nearly flat, and the horizon problem, which questions how different regions of the universe, which are far apart, have similar temperatures. By proposing that inflation caused distant regions of space to come into contact and then separate before cooling down, the inflationary model provides a coherent explanation for these phenomena. Moreover, the inflationary bubble also contributes to our understanding the large-scale structure of the universe. The quantum fluctuations that occur during inflation are believed to be the seeds of all current galaxies and cosmic structures. As the inflationary bubble expanded, tiny variations in density were stretched across the universe, leading to the gravitational clumping that eventually formed galaxies and clusters of galaxies. Thus, the inflationary theory not only helps to explain the conditions of the early universe, but also lays the groundwork for the formation of the structures we see today. In addition to these insights, the inflationary model has generated numerous predictions that have been tested and supported by observational evidence. For instance, measurements of the cosmic microwave background radiation, which is the afterglow of the Big Bang, show patterns consistent with inflationary predictions. These patterns include slight anisotropies that correspond to the quantum fluctuations that were stretched during inflation, providing further validation of the theory. Furthermore, the significance of the inflationary bubble extends into the realms of fundamental physics, as it raises questions about the nature of the universe itself, including concepts like multiverses, where our universe might be just one of many, each with its own set of expansion of the universe just after the Big Bang plays a crucial role in how galaxies and large-scale structures form. It sets the stage for the universe we see today by stretching tiny quantum fluctuations across vast distances. These fluctuations, which are essentially tiny variations in density, become the seeds for all structures in the universe. As the universe expands, matter leading to the clumping of gas and dark matter, this clumping is fundamental for galaxy formation, because without the initial density fluctuations created during inflation, the matter in the universe would be distributed too evenly, making it difficult for galaxies to form. As regions of space evolve, gravity amplifies these fluctuations. eventually leading to the formation of stars, galaxies, and clusters of galaxies. The gravitational attraction pulls matter together, and over time, this process results in the complex web of galaxies. Web, the large-scale structure of the universe, is characterized by filaments of galaxies interconnected by vast voids. This structure is a direct consequence of the density variations that inflation introduced. Furthermore, inflation also affects the rate of expansion of influences how structures grow over time. A faster expansion during the early universe means that matter had less time to spread out evenly, enhancing the chances of forming the dense areas from which galaxies and clusters could emerge. Researchers have used computer simulations to model this process, and they show that the inflationary period is essential for creating the large-scale structure we observe, confirming the predictions made by cosmological theories. Inflationary models not only explain the uniformity of the cosmic microwave background radiation, but also provide insights into the distribution of galaxies across the universe. In essence, inflation is a key player in the cosmic drama of structure formation. Without it, the universe would not have the rich tapestry of galaxies, clusters, and voids that we see today. Thus, studying inflation helps us understand to shape the cosmos. Cosmic inflation and dark energy, while distinct concepts in cosmology, are thought to be interconnected in intriguing ways, both addressing the expansion of the universe, but from different perspectives. Cosmic inflation refers to a rapid exponential expansion of the universe that occurred just after the Big Bang, approximately 10 to the minus 30 seconds after it began. This theory helps explain the uniformity of the universe we observe today, as well as the distribution of cosmic structures such as galaxies and clusters, by smoothing out any irregularities leading to the even distribution of matter and energy we see across vast distances. On the other hand, dark energy is the mysterious force driving the accelerated expansion of the universe we observe today, which began around 5 billion years ago. While inflation occurred during the very early universe, dark energy is acting on the universe now, suggesting that these two phenomena, though separated by billions of years, may have a deeper connection. One of the significant threads linking cosmic inflation to dark energy lies in the nature of the vacuum state in quantum field theories. During inflation, the energy density of the vacuum was incredibly high, leading to the rapid expansion. In this context, some theorists propose that the same vacuum energy responsible for inflation could also be related to dark energy, as both involve the energy of empty space. Essentially, if the universe's expansion was driven initially by this vacuum energy during inflation, it raises the question of whether the vacuum energy persists today, manifesting itself as dark energy. This idea suggests that dark energy could be a remnant of the inflationary period, providing a cosmic continuity from the very early stages of the universe to its current accelerated expansion. Furthermore, scientists are exploring models of inflation that incorporate dark energy, such as those involving scalar fields. These models suggest that the dynamics of these fields could lead to both the inflationary phase and the subsequent dark energy dominated phase of the universe's evolution. The relationship between these two concepts remains an active area of research, as understanding this connection could offer insights into the fundamental structure of our universe. Moreover, researchers are investigating whether the properties of dark energy might influence the specifics of how inflation occurred, including how quickly it happened and what the final state of the universe will be. Theories like the quintessence model propose that dark energy is not a constant, but rather a dynamic field that evolves over time, which could also tie back to the conditions present during inflation. In conclusion, while cosmic inflation and dark energy, cosmic inflation is a fascinating phase in the early universe, occurring just a fraction of a second after the Big Bang. And it plays a crucial role in shaping the structure of the cosmos we observe today. During this brief but intense period, the universe underwent exponential expansion, stretching from subatomic scales to astronomical sizes in an incredibly short time. This rapid inflation smoothed out any irregularities, creating a nearly uniform universe. However, it also set the stage for the density fluctuations that would eventually lead to the formation of galaxies and large-scale structures. As inflation caused the universe to expand, tiny quantum fluctuations in the density of matter were stretched to macroscopic scale. These fluctuations, initially at the quantum level, became imprinted in the fabric of space-time. When inflation ended, the energy driving the expansion converted into particles and radiation, leading to the creation of the hot, dense state of matter that filled the universe. The regions where matter was slightly more densely packed began to gravitationally attract surrounding matter, gradually growing into the galaxies, clusters, and superclusters we see today. The density fluctuations, which inflation magnified, were crucial for the subsequent evolution of the universe. They provided the seeds for gravitational collapse, as areas of slightly higher density could influence their surroundings, pulling in more matter over time. This process was essential for the formation of the cosmic web, a vast network of galaxies and dark matter that permeates the universe. Observations of the cosmic microwave background radiation, which is the afterglow of the Big Bang, provide evidence of these density fluctuations, revealing a pattern that matches theoretical predictions from inflationary models. Moreover, the specific characteristics of these fluctuations, such as their amplitude and spectrum, can tell us a lot about the physics of inflation itself. Scientists use data from missions like the Planck satellite to analyze the cosmic microwave background, which helps to refine our understanding of the inflationary process and its implications for the early universe. The patterns we observe in the cosmic microwave background and the distribution of galaxies today are deeply connected to those tiny fluctuations created during inflation, illustrating how a brief moment in time can have lasting effects on the vast structure of the universe. In essence, cosmic. Inflation not only smoothed out the universe, but also seeded it with the density fluctuations necessary for all the complexity we see around us. From the formation of stars to the clustering of galaxies, painting a dynamic and intricate picture of cosmic evolution that continues. Understanding of the universe. The inflationary model, a theory that suggests the universe underwent a rapid expansion just after the Big Bang, has been widely accepted in cosmology. Yet it is not without its challenges and criticisms. One of the primary challenges is the question of how inflation started in the first place. The model relies on the existence of a scalar field, often called the inflaton, but the nature of this field is still unknown, and no definitive evidence for it has been found. This leads to skepticism among some scientists, who argue that without a clear understanding of the mechanism that triggers inflation, the model remains speculative. Moreover, inflation predicts a nearly uniform universe, but there are discrepancies when it comes to the large-scale structure of the universe. Observations suggest there are more variations in the density of matter than the inflationary model would predict. Critics point to this as a sign that while inflation may explain some features of the cosmos, it may not account for all of them, indicating that our understanding of the early universe might still be incomplete. Another point of contention is the fine-tuning problem, which arises from the fact that inflation seems to require very specific conditions to work effectively. Proponents of the model must explain why the universe started in such a finely tuned state. This has led some physicists to argue that the inflationary model might be too reliant on initial conditions that seem improbable, raising questions about its overall validity. Additionally, the model has been criticized for its lack of predictive power. While inflation does provide a framework for understanding certain observations, such as the cosmic microwave background radiation, it has yet to make predictions that can be tested with precision. As new observational data comes in, some of the predictions made by inflationary theory have not matched observations, prompting some researchers to explore alternative theories that might better explain the data. Lastly, the concept of multiple inflationary events, which suggests that inflation could occur repeatedly in different regions of space, complicates the scenario even further. This leads to the idea of a multiverse, where our observable universe is just one bubble among many. While this is an intriguing idea, it raises philosophical questions about the nature of reality and the limits of scientific. The multiverse hypothesis lacks empirical support, and many scientists feel it strays too far from testable science, leaning more into the realm of speculation. As cosmologists continue to gather more data from missions like the James Webb Space Telescope and ongoing observations of the cosmic microwave background, the dialogue around the inflationary model, the concept of eternal inflation, is a fascinating extension of the standard inflationary model, which was proposed to explain the rapid expansion of the universe after the Big Bang. In standard inflationary models, the universe experiences a brief but incredibly rapid expansion in its earliest moments, leading to a uniform and isotropic cosmos. However, eternal inflation takes this idea further, suggesting that inflation can continue indefinitely in certain regions of the universe, leading to a multiverse scenario where different parts of the universe undergo inflation at different rates. This means that while some regions of space may cool and settle into a more stable state, others can remain in the inflationary phase, creating a patchwork of universes, each with its own unique properties. In eternal inflation, the inflaton field, which is responsible for driving inflation, does not settle into a single state everywhere at once. Instead, due to quantum fluctuations, some regions of space can fall out of inflation while others continue to inflate. This idea introduces a significant departure from the standard model, where inflation is a one-time event that occurs uniformly across the universe. In eternal inflation, as different regions of space stop inflating and form, these bubbles can have different physical laws, constants, and even dimensions, resulting in a vast and diverse multiverse. This concept also raises intriguing questions about the nature of time and space. In eternal inflation, time may not flow uniformly across the entire universe. Some regions may experience time differently, depending on their inflationary state. This means that while one bubble universe might evolve into a galaxy, rich environment, another might remain in a state of perpetual inflation, never allowing for the formation of stars or planets. Consequently, this leads to a rich tapestry of possible realities existing simultaneously, each shaped by its own unique conditions and histories. Eternal inflation has also been a topic of debate among physicists and cosmologists, with some arguing that it could provide answers to fundamental questions about the fine-tuning of the universe. For instance, the varying constants and laws in different bubble universes may help explain why our universe appears so well suited for life. If many universes exist, with some having conditions that support life and others that do not, this could account for the apparent improbability of our own universe's properties. The anthropic principle, which suggests that we can observe and question the universe because we are here, might find a place in this multiverse framework, where only certain conditions. Eternal inflation is a fascinating and complex theory in cosmology, suggesting that our observable, just a tiny part of a much larger multiverse, where regions of space continue to inflate indefinitely, creating pockets of space that stop inflating and form distinct universes. So, to detect the occurrence of eternal inflation, scientists look for specific observational signatures that can provide clues about this process. One of these signatures is the presence of certain patterns in the cosmic microwave background, or COM radiation, which is the afterglow of the Big Bang, as fluctuations in the temperature and polarization of the key me can reveal the influence of quantum fluctuations that happen during inflation. These fluctuations could leave imprints on the COM that indicate rapid expansion and may also show a distinct non-Gaussian distribution, which would suggest that different regions of space had different histories of inflation. Another potential signature is the existence of primordial gravitational waves, ripples in space-time caused by the stretching and squeezing of space during inflation. If eternal inflation occurred, it could lead to a measurable background of gravitational waves, which researchers are actively searching for using observatories like LIGO and Virgo, as these waves may carry information about the energy scales of inflation and the dynamics of the early universe. Furthermore, scientists also consider the possibility of detecting large-scale structures in the universe that could hint at eternal inflation. For instance, if eternal inflation is true, it might produce a variety of bubble universes, each with different physical laws, and the interactions between these bubbles could leave observable effects, such as collisions or boundaries between different regions, known as bubble collisions, which could create unique signatures in the distribution of galaxies and cosmic structures. Another intriguing aspect is the study of the distribution of galaxies across the universe. If eternal inflation occurred, we might see an unusual clustering pattern or voids that are inconsistent with standard models of cosmic evolution. This could indicate that different regions have different histories of inflation, thereby supporting the idea of a multiverse. Moreover, scientists are also examining the isotropy and homogeneity of the universe, which are fundamental assumptions in cosmology. If eternal inflation is at play, it could lead to observable deviations from these assumptions, such as anisotropies in the CORM or the universe, which would challenge our current understanding of cosmological principles. The search for these signatures is ongoing, and as technology advances, astronomers and physicists are developing more sensitive instruments that can detect these subtle. The Lyman alpha forest is a fascinating phenomenon observed in the spectra of distant quasars, which are incredibly bright and distant objects powered by supermassive black holes. When we look at these quasars, we see numerous absorption lines, which are created by hydrogen gas in the intergalactic medium. And this collection of lines is what we call the Lyman alpha forest. Scientists have discovered that these absorption lines can tell us a great deal about the universe's structure and the conditions during its early moments. The Lyman alpha forest is particularly exciting for cosmologists because it serves as a rich source of information about the density fluctuations in the universe, which are believed to have been shaped by inflation, a rapid expansion that occurred just after the Big Bang. Inflation theory posits that, for a brief moment, the universe expanded exponentially, smoothing out any irregularities and leading to the uniform cosmos we see today. By studying the distribution of these Lyman alpha absorption lines, scientists can map the density of hydrogen in the universe at different distances, which corresponds to different times in the universe's history. This mapping allows researchers to look back in time and observe how matter has clumped together, revealing the underlying structure of the universe. When scientists analyze the Lyman alpha forest, They are particularly interested in how the absorption lines vary with redshift, which tells us how far away the quasar is, and therefore how early in the universe's history we are observing. Through statistical methods, researchers can compare the observed distribution of these lines to predictions made by inflationary models. If the patterns match, it supports the idea that inflation occurred. Conversely, if the patterns deviate significantly from what is expected, it could indicate that our understanding of inflation needs to be revised. Moreover, the Lyman alpha forest can also help scientists probe the physics of dark matter and dark energy, which are critical components of our universe. By understanding how these elements influence the structure formation observed in the Lyman alpha forest, researchers can gain insights into the fundamental forces that shaped the cosmos. This connection between the Lyman alpha forest and inflation is a prime example of how astronomers can use light from the distant past to unravel the mysteries of our universe, piecing together the puzzle of its origins and evolution. The interplay between the observed structures in the Lyman alpha forest and theoretical models of inflation holds the potential to deepen our understanding of the universe, offering clues about the very fabric of space and time. Neutrinos, those elusive, nearly massless particles, play a fascinating role in the context of cosmic inflation and the early universe. Their contributions often overlooked due to their weak interactions with matter. In the moments just after the Big Bang, when the universe was a hot, dense soup of particles, neutrinos were produced in vast quantities during a process called nucleosynthesis, which occurred within the first few minutes of the universe's existence. This period was crucial for the formation of the first atomic nuclei, including hydrogen and helium, and neutrinos, being so abundant, contributed to the energy dynamics of the universe at that time, influencing the matter content and the overall evolution of the cosmos. As cosmic inflation took hold, stretching the fabric of space-time at an exponential rate, neutrinos played a subtle yet important role in the cooling of the universe. Their weak interactions meant they could escape from the hot plasma more easily than other particles, helping to carry away energy and contributing to the cooling process. This cooling was essential for the formation of matter structures, as it allowed protons and neutrons to combine into nuclei, setting the stage for the formation of atoms, and eventually the galaxies and stars we see today. The presence of neutrinos during these early moments also influenced the cosmic microwave background radiation, a relic of the early universe, which provides a snapshot of the cosmos when it was just about 380,000 years old. Furthermore, neutrinos are key players in our understanding of the universe's evolution, as they can provide insights into the conditions of the early universe and the processes that governed its expansion. The study of neutrinos, particularly through experiments designed to detect them, helps scientists refine their models of cosmic inflation and the Big Bang. Observing these tiny particles allows researchers to gather information about the universe's density temperature, and the rates of expansion during its formative moments. In the context of cosmic inflation, neutrinos can also shed light on the nature of dark matter and dark energy, two of the most mysterious components of the universe, by helping to inform theories that attempt to explain their existence and behavior. In summary, neutrinos, though often considered insignificant due to their weak interactions, are crucial for understanding the dynamics of the early universe, influencing the processes of nucleosynthesis, cooling, and the formation of structures that would eventually lead to the universe. Today, their investigation not only enhances our comprehension of cosmic inflation, but also deepens our insight into the fundamental forces and particles that shape inflation theory, which proposes a rapid expansion of the universe just after the Big Bang, plays a crucial understanding of cosmic topology, or the large-scale structure of the universe. According to inflationary models, the universe expanded exponentially, smoothing out any irregularities and allowing for a more uniform distribution of matter and energy. This rapid inflation means that tiny quantum fluctuations, which occurred during this early phase, became stretched across vast distances, leading to the formation of galaxies and large-scale structures we observe today. As a result, inflationary theory helps us understand why the universe appears so homogeneous and isotropic on large scales, despite the presence of local structures like galaxies and galaxy clusters. Moreover, inflation theory suggests that the universe could have various topological shapes, such as flat, open, or closed geometries, depending on the density of matter and energy within it. These shapes influence how we perceive the universe's overall structure and can lead to different cosmic outcomes. For instance, a flat universe, which is supported by current observations of the cosmic microwave background radiation, implies that the universe will expand forever at a steady rate, whereas a closed universe would eventually stop expanding and begin to contract. Furthermore, the study of cosmic topology under the framework of inflation theory has led scientists to explore concepts like multi-connectedness, where our universe could be a part of a larger, more complex structure. This idea raises fascinating questions about the possibility of other dimensions or parallel universes which could exist alongside our own. By examining how inflation influences these topological properties, researchers can investigate how the universe's shape affects the paths that light takes, which is crucial for understanding phenomena like gravitational lensing and cosmic microwave background anisotropies. In addition, inflationary models provide predictions about the distribution of galaxies and matter in the universe. If inflation occurred, we would expect to see a specific pattern in the cosmic web, characterized by the clustering of galaxies along filaments with vast voids in between. This web-like structure is a direct consequence of the initial conditions set by inflation. And studying it helps astronomers map the universe's topology more accurately. By combining observations from telescopes with theoretical models, scientists can refine their understanding of cosmic topology and how it relates to the fundamental physics of the universe. Ultimately, the interplay between inflation theory and cosmic topology opens up new avenues for exploration, pushing the boundaries of our knowledge about the universe's structure and behavior. It invites researchers to ask deeper questions about the nature of cosmic inflation, a theory that suggests the universe underwent an extremely rapid expansion just after the Big Bang, plays a significant role in discussion about the multiverse hypothesis. Of many, perhaps infinitely many, universes that exist simultaneously, the relationship between these two ideas stems from the implications of inflationary theory, which can lead to scenarios where multiple universes are formed, each with its own distinct physical properties. When we think about cosmic inflation, it's essential to understand that this rapid expansion smoothed out the universe, creating the large-scale structure we see today, while also potentially allowing for regions of space to stop inflating at different times. This means that some areas could become separate, independent universes, effectively giving rise to a kind of cosmic bubble scenario, where each bubble constitutes a different universe with different rules or constants of nature. In this framework, the multiverse hypothesis can be seen as a natural extension of cosmic inflation. If inflation can happen repeatedly in different regions of space, it suggests that there are regions that expand into separate bubbles, each with its own unique set of physical laws, which could lead to a variety of outcomes, from universes with very different properties to our own. This concept of eternal inflation suggests stops, but rather continues in some regions, creating an endless array of universes, which can have vastly differing characteristics. Additionally, the multiverse hypothesis addresses some fundamental questions in cosmology, such as why our universe appears fine, tuned for life. In a multiverse scenario where countless universes exist, it's statistically probable that at least some of them would have the right conditions to support life, while others might not. This idea helps to explain the apparent fine-tuning without requiring a special explanation for our own universe, as we simply happen to live in one of the many that is conducive to life. Moreover, it's worth noting that the multiverse hypothesis is still a topic of debate among physicists, as it raises questions about testability and falsifiability. Key principles in the scientific method. Critics argue that if there are countless universes and we can only observe our own, then the multiverse theory might fall outside the realm of empirical science, making it difficult to verify or disprove. Proponents, on the other hand, point to the mathematical frameworks that arise from inflationary theory and quantum mechanics, suggesting that inflationary models which propose a rapid expansion of the universe in its earliest moments, play a crucial role in understanding the distribution of galaxies across the cosmos. According to these models, the universe underwent a phase of exponential growth, stretching tiny quantum fluctuations in the density of matter and energy into scales that eventually gave rise to the large-scale structure we observe today. As the universe expanded, these fluctuations, which were once minuscule, became the seeds for all cosmic structures, including galaxies. The key idea here is that the uneven distribution of matter, created during inflation, led to areas of higher density where galaxies could form and clusters could develop, while less dense regions would have fewer galaxies. The theory suggests that the variations in density arising from quantum fluctuations were not uniform, resulting in a web-like structure known as the cosmic web, characterized by filaments of galaxies and vast voids in between. These density variations eventually influenced how matter clumped together, leading to the formation of galaxies, galaxy clusters, and superclusters. Observations of the cosmic microwave background radiation, which is the afterglow of the Big Bang, provide a snapshot of these early fluctuations, revealing patterns that match the predictions made by inflationary models. Furthermore, simulations based on inflationary theory have shown that the statistical properties of these fluctuations are consistent with what we see in the distribution of galaxies today. For instance, the distribution is not random. Instead, it reflects a structured pattern where galaxies tend to align along filaments, while empty regions exist as voids. These simulations also help researchers understand how galaxies grow and evolve over time, with the initial density fluctuations leading to gravitational attraction, which pulls matter together, forming stars, galaxies, and eventually the complex structures. In addition, inflationary models offer explanations for the relative abundance of different types of galaxies and the large-scale patterns in their distribution. By considering how the universe expanded and cooled, these models account for the variety of galaxy shapes and sizes we observe, such as spiral galaxies, elliptical galaxies, and irregular galaxies. The process of galaxy formation is influenced not only by the initial conditions set by inflation, but also by subsequent interactions, mergers, and environmental factors, which are all rooted in the conditions established during that rapid early expansion. In summary, inflationary models provide a framework for understanding why galaxies are distributed as they are, linking the universe's earliest moments to the complex web of structures we see today, and by doing so, they deepen our understanding of inflation in the context of cosmology. Rapid exponential expansion of the universe that occurred just after the Big Bang, and understanding its implications can lead us to fascinating insights about the fate of the universe. This theory, proposed by Alan Guth in the 1980s, suggests that the universe expanded faster than the speed of light within a tiny fraction of a second, smoothing out any irregularities and leading to the uniform cosmic microwave background we observe today. The implications of inflation are profound, as they suggest that the universe is much larger than the observable portion we can see, potentially containing regions that are completely disconnected from our own, which raises intriguing questions about the nature of space and time. One major implication of inflation is that it provides a framework for understanding the large-scale structure of the universe. Tiny quantum fluctuations during the inflationary period were stretched across the universe, seeding the formation of galaxies and clusters of galaxies. This means that the structure we observe today, from galaxy distributions to cosmic web formations, is a direct result of these early inflationary processes, connecting the very small to the very large in a way that continues to puzzle and excite astronomers and physicists alike. Additionally, inflation has consequences for the ultimate fate of the universe. Depending on the specific parameters of inflation, such as the energy density of the universe and the nature of dark energy, the universe could evolve in different ways. If dark energy continues to dominate, the universe may expand forever, leading to a scenario known as the Big Freeze, where galaxies drift apart, stars burn out, and the universe becomes cold and dark. On the other hand, if certain conditions are met, a big crunch could occur, where the expansion eventually halts and reverses, collapsing back into a singularity. Moreover, inflation suggests that our universe might be part of a multiverse, a collection of many universes, each with different physical laws and constants. This idea arises from the concept of eternal inflation, where some regions of space stop inflating while others continue. If this is true, it leads to the possibility that the fate of our universe is just one of many, each with its own unique end, which could range from end. Furthermore, the implications of inflation extend to the very fabric of reality itself and how we understand time and space. The rapid expansion could mean that regions of space are causally disconnected, which challenges our notions of what it means for inflation. A theory that describes the rapid expansion of the universe just after the Big Bang plays a significant role in shaping the isotropy of the cosmos. Isotropy refers to the idea that the universe looks the same in all directions, which is one of the fundamental assumptions in cosmology. Under the influence of inflation, the universe underwent an exponential stretch, smoothing out any irregularities, and this rapid expansion helps explain why the cosmic microwave background radiation, which is the afterglow of the Big Bang, appears remarkably uniform. Essentially, inflation takes tiny quantum fluctuations and stretches them across vast distances, which contributes to the homogeneous and isotropic nature we observe today. The process of inflation is thought to have occurred within a fraction of a second after the universe began, and during this time, the universe expanded faster than the speed of light. This incredibly swift growth helped to erase any initial inhomogeneities or anisotropies, leading to a more uniform distribution of matter and energy. As a result, when we look out into space, we see that the universe does not favor any particular direction. And this isotropy is a cornerstone of the cosmological principle, which states that the universe is the same everywhere on large scales. Moreover, inflation predicts that small perturbations or fluctuations would still exist after this smoothing process. And these perturbations eventually grew into the large-scale structures we see today, such as galaxies and galaxy clusters. The uniformity we observe in the cosmic microwave background radiation with its slight temperature variations supports the inflationary model, as these variations represent the seeds of future structure formation. But they do not indicate any significant anisotropy. In essence, without the mechanism of inflation, we might expect to see much more variation in the universe's large scale structure, leading to a cosmos that appears clumpy or uneven. Instead, inflation provides a framework that explains both the uniformity we observe and the slight irregularities that allow for the rich structure of the universe to emerge over billions of years. Therefore, the impact of inflation on isotropy is profound, as it not only sets the stage for a uniform universe, but also allows for the development of the intricate web of galaxies, stars, and other cosmic phenomena that we study today. The isotropy of the universe, thus, is intimately linked to the dynamics of inflation, making it a key area of interest in modern cosmology. As scientists continue to seek a deeper understanding of the early universe and inflationary theory, which proposes a rapid expansion of the universe in its earliest moments, has significantly transformed our understanding of cosmology, offering a framework that addresses several fundamental issues that arose from the Big Bang model. Before inflation was introduced, the Big Bang theory struggled to explain certain large-scale structures observed in the universe, such as the uniformity of the cosmic microwave background radiation, which is remarkably homogeneous across vast distances despite that. Inflationary theory provides a solution to this puzzle, suggesting that the universe underwent an exponential expansion, stretching tiny quantum fluctuations to cosmic scales, thus creating the uniformity we observe today. Moreover, inflation helps to explain the distribution of galaxies and large-scale structures. As the universe expanded rapidly, the tiny fluctuations in density that existed in the early universe were amplified, leading to the formation of the galaxies we see today. This theory aligns with observations made by satellite missions such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, which have measured the cosmic microwave background in detail, confirming the predictions of inflation regarding the universe's flatness and homogeneity. Additionally, inflationary theory has implications for the concept of cosmic topology, suggesting that the universe may not be as simple as a flat, infinite space, but could be part of a more complex structure, potentially with multiple connected universes. This idea challenges our traditional views of space and opens up exciting possibilities for understanding the universe's shape and overall geometry. Furthermore, inflationary theory has led to the development of various models, such as hybrid inflation and chaotic inflation, which explore the potential sources of inflation and how they could relate to fundamental physics, including theories of quantum gravity. These models have fueled discussions about the early universe's energy scales and the types of particles that may have played a role in driving inflation, thus bridging cosmology with particle physics. As researchers continue to study the implications of inflationary theory, they also delve into its possible connections to dark energy and the universe's accelerated expansion, which suggests that the inflationary phase might have some commonality with the forces driving current cosmic acceleration. Investigating these links could provide deeper insights into the fundamental nature of the universe and the forces that shape it. In summary, inflationary theory has not only resolved key puzzles in cosmology, but has also opened up new avenues of research, inviting scientists to explore the universe's earliest moments. It's to test inflationary models astronomers employ several sophisticated methods, each designed to probe different aspects of the early universe. One of the primary techniques involves studying the cosmic microwave background, or CUM, which is the afterglow radiation from the Big Bang permeating the universe. By analyzing the tiny temperature fluctuations in the CUM, scientists can gather crucial information about the density and distribution of matter in the early universe, which helps to confirm or refute various inflationary models. Instruments like the Wilkinson Microwave Anisotropy Probe, or BOOMAP, and the Planck satellite have provided detailed maps of these fluctuations, allowing astronomers to compare their observations with predictions made by different inflationary scenarios. Another method involves the observation of large-scale structures in the universe, such as galaxies and clusters of galaxies. The distribution and formation of these structures can provide insights into the conditions of the universe shortly after inflation. By studying the way these structures have evolved over time, astronomers can infer the nature of the forces at play during inflation, helping to distinguish between different models. Surveys like the Sloan Digital Sky Survey, or SSS, have been instrumental in providing this data. Gravitational waves, ripples in space-time caused by massive cosmic events, are another exciting avenue of research. Inflationary models predict that the rapid expansion of the universe would generate gravitational waves, which could be detected by observatories like LIGO and Virgo. While direct detection of gravitational waves from inflation remains a challenge, the indirect evidence of primordial gravitational waves can significantly constrain inflationary models. Additionally, astronomers examine the distribution of primordial elements, such as hydrogen and helium, formed during Big Bang nucleosynthesis. The ratios of these elements, as predicted by inflationary models, can be tested against observations of ancient gas clouds and the chemical composition of the oldest stars in the universe. This method allows scientists to validate aspects of inflation by ensuring that the predicted element abundances match what we observe in the cosmos. Furthermore, computer simulations play a crucial role in testing inflationary models. By creating detailed simulations of the early universe based on different inflation scenarios, astronomers can visualize and predict how the universe would evolve under various conditions. These simulations can then be compared with observational data to assess the validity of the models. Such computational approaches help bridge the gap between theoretical predictions and practical observations, allowing for a more comprehensive understanding of inflation. In recent years, advances in observational technology, such as high-resolution telescopes and sensitive detectors, have vastly future observational missions are gearing up to detect gravitational waves from inflation, a period that occurred just moments after the Big Bang, characterized incredibly rapid expansion of the universe. During this brief but transformative phase, the fluctuations in the fabric of space-time caused by quantum effects generated gravitational waves, which are ripples that travel through space and time. Detecting these gravitational waves is crucial because they can provide insights into the conditions of the early universe, offering clues about what happened during inflation and possibly revealing information about physics beyond the standard model. One of the most promising future missions is the Laser Interferometer Space Antenna, or LISA, which is set to be launched in the 2030s. LISA will be a space-based observatory, utilizing 3 satellites positioned in a triangular formation, orbiting the Earth and measuring distortions in space-time caused by passing gravitational waves. The frequency range that LISA will be sensitive to is particularly well suited for detecting the low-frequency gravitational waves that are expected from inflation, as these waves stretch across the cosmos, carrying with them the imprint of the universe's rapid expansion. Another exciting initiative is the proposed Cosmic Explorer, a ground-based observatory which aims to complement LISA by targeting higher frequency gravitational waves, which are produced from various astrophysical sources, including the merger of black holes and neutron stars. Cosmic Explorer would utilize a large, advanced interferometer, significantly improving sensitivity compared to existing facilities like LIGO, allowing it to explore the gravitational wave background, which is thought to include signals from the inflationary epoch. Additionally, the European Space Agency's proposed mission, the Gravitational Wave Observatory, known as the Advanced LIGO, is also focused on detecting gravitational waves from inflation. By collaborating with existing observatories, future missions hope to create a network of detectors that will enhance the chances of capturing these elusive signals. The combination of different frequencies and observational techniques will provide a more comprehensive view of gravitational waves, helping scientists piece together the timeline of the universe's evolution. Moreover, the study of cosmic microwave background radiation, or CMB, is another avenue being explored to glean information about gravitational waves from inflation. While not a direct method for detecting gravitational waves, the CMB carries imprints of gravitational waves in the form of B-mode polarization patterns. Future missions that map the CALM, such as the Simons Observatory and the Coombs 4 project, aim to search for these patterns, which would indicate the presence of gravitational waves from inflation, the significance of the scalar field. In inflationary models lies in its role as a fundamental component that drives the rapid expansion of the universe during the inflationary period, which is believed to have occurred just after the Big Bang. In these models, the scalar field represents a form of energy that permeates space, often referred to as inflaton. This inflaton field is responsible for creating a repulsive gravitational effect, which leads to the exponential growth of the universe's size. During inflation, tiny quantum fluctuations in this scalar field can be stretched across vast distances, eventually leading to the formation of the large-scale structure we observe today, such as galaxies and galaxies. Moreover, the dynamics of the scalar field, specifically its potential energy and its interactions, determine the rate of inflation and the uniformity of the cosmic microwave background radiation, which provides crucial evidence for inflationary theory. The smoothness and flatness of the universe observed today, as well as the slight anisotropies in the cosmic microwave background, can be explained by the properties of the scalar field that governed the inflationary phase. In addition, the scalar field's characteristics can influence the spectrum of primordial gravitational waves, which are ripples in space-time that are predicted to have been generated during inflation. Detecting these gravitational waves would provide strong evidence for inflationary models and help scientists learn more about the conditions in the early universe. The concept of the scalar field also opens the door to various theoretical frameworks, including string theory and supersymmetry, which aim to unify the fundamental forces of nature and explain the underlying physics of the inflaton field. As researchers continue to explore the implications of scalar fields in cosmology, they are investigating different types of inflationary models that involve various potential forms for the scalar field. This research could lead to a deeper understanding of dark energy, the mysterious force that is driving the current accelerated expansion of the universe. This interplay between scalar fields, inflation, and cosmic evolution remains a vibrant area of inquiry, pushing the boundaries of our understanding of the universe's origins and its ultimate fate. Inflation, a theory that explains the rapid expansion of the universe just after the Big Bang, interacts intriguingly with theories of quantum gravity, which seek to reconcile the principles of quantum mechanics with general relativity. In the context of inflation, the universe experienced an exponential growth, smoothing out any irregularities and leading to the large-scale structure we observe today. This rapid expansion can be described using quantum field theory, where fields, rather than particles, are the fundamental entities. During inflation, quantum fluctuations in these fields can create tiny variations in density, which eventually seed the formation of galaxies. The interplay between inflation and quantum gravity arises from the need to understand how these fluctuations are generated and how they behave in a universe that is expanding so rapidly. In classical general relativity, gravity is described by curved space-time. But at quantum scales, things become much more complicated, as gravity itself must also follow the rules of quantum mechanics. One of the key challenges is to describe how gravitational waves, ripples in space-time produced by massive objects, behave in an inflating universe. Some theories of quantum gravity, like string theory, suggest that space-time may have a discrete structure at very small scales, which could influence the dynamics of inflation. Moreover, the energy conditions during inflation, which are dictated by the inflaton field, the hypothetical scalar field thought to drive inflation, can lead to interesting scenarios when combined with quantum gravity. For example, some models propose that the inflaton field might have a non-trivial topological structure, leading to different outcomes in the early universe's evolution. In such scenarios, quantum fluctuations could give rise to different inflationary trajectories, potentially explaining the observed uniformity of the cosmic microwave background radiation. Additionally, the concept of vacuum energy, which plays a crucial role in both inflation and quantum gravity, is another layer of complexity. Vacuum energy is thought to drive the accelerated expansion of the universe, and understanding its origins requires. This is where theories like loop quantum gravity come into play, as they attempt to describe space-time at the quantum level, possibly allowing for a more comprehensive understanding of inflation's dynamics. The concept of the multiverse, which emerges from some inflationary models, also raises interesting questions when combined with quantum gravity. If our universe is just one of many, each potentially governed by different physical laws, how does that interplay with the fabric of space-time described by quantum gravity? This creates a rich field for theoretical exploration as scientists aim to understand how these symmetry breaking plays a crucial role in our understanding of the early universe, particularly during the period known as cosmic inflation, which is believed to have occurred just after the Big Bang. In simple terms, symmetry breaking refers to a process where a system that is initially symmetrical ends up in a state that is not symmetrical. This concept is significant in various fields of physics, but in the context of inflation, it helps explain how the universe transitioned from a hot, dense state to the vast cooler cosmos we see today. During the inflationary period, the universe underwent an exponential expansion, stretching space itself at an incredible rate. This rapid expansion, however, could not have happened without a mechanism to drive it. Here, symmetry breaking comes into play. Initially, this inflaton field can be thought of as being in a symmetrical state, where all configurations are equally likely. However, as the universe expanded, the inflaton field's value began to settle into a specific configuration, breaking the symmetry. This symmetry breaking is essential because it leads to the release of energy, which fuels the inflationary expansion. When the inflaton field settles into a lower energy state, it results in a rapid increase in the size of the universe, smoothing out any irregularities and creating the large-scale structure we observe today. Additionally, as the inflaton field transitions, quantum fluctuations can occur, which are tiny variations in energy density. These fluctuations are crucial because they serve as the seeds for the later formation of galaxies and other cosmic structures. Moreover, symmetry breaking also has implications for the fundamental forces and particles in the universe. As the inflationary phase ends, the energy stored in the inflaton field can be converted into particles, leading to a reheating phase, where the universe becomes filled with particles and radiation. This process is vital for the creation of the matter that eventually forms stars, galaxies, and everything we see in the universe today. In summary, symmetry breaking during inflation is a pivotal mechanism that not only explains the dynamics of the universe's rapid expansion, but also sets the stage for the formation of structure in the cosmos, making it an integral part of our understanding of the early universe. The interplay between symmetry, energy dynamics, and the resulting cosmic growth is a fascinating area of study, revealing the underlying complexities of how the advancements in technology have significantly transformed the study of cosmic inflation, a concept that describes the rapid expansion of the universe just after the Big Bang. With the development of more sophisticated telescopes, both ground-based and space-based, astronomers can now observe distant cosmic backgrounds, allowing them to gather data that was previously out of reach. For example, the launch of the Planck satellite in 2009 provided high-resolution measurements of the cosmic microwave background, or COM, which is the afterglow of the Big Bang. This data has been crucial in testing predictions made by inflationary models, helping scientists understand the initial conditions of our universe. Moreover, advancements in computer simulations have opened new doors for researchers, enabling them to model the complex physical processes that occurred during inflation. These simulations help scientists explore various inflationary scenarios and their implications for the universe's large-scale structure. As computational power has increased, simulations have become more detailed and accurate, allowing for a better understanding of how different inflationary models could lead to the observable universe we see today. In addition to telescopes and simulations, innovations in detector technology have also played a vital role. New detectors, such as those used in interferometers, can measure minute fluctuations in the COM with incredible precision. This sensitivity is crucial for detecting the faint gravitational waves that some inflationary models predict were produced during the rapid expansion. The detection of these waves would provide strong evidence for inflation theory, and the technology to achieve this is advancing rapidly. Furthermore, machine learning and artificial intelligence are being integrated into the analysis of astronomical data, helping researchers sift through vast amounts of information more efficiently. These technologies can identify patterns and correlations in the data that might not be immediately obvious to human analysts. By leveraging these advanced tools, scientists can refine their understanding of cosmic inflation and its implications for the evolution of the universe. Additionally, advancements in particle physics, including the discovery of new particles and interactions in high-energy experiments, also inform our understanding of inflation. These discoveries can provide insights into the fundamental forces at play in the early universe, shedding light on how inflation might have occurred. The interplay between cosmology and particle physics is becoming more pronounced, as both fields work together to unravel the mysteries of the cosmos. As technology continues to evolve, the tools and methods available to study cosmic inflation will only become more sophisticated. This ongoing progress ensures that our understanding of the universe's earliest moments will continue to deepen as new data and theories emerge. The fusion of innovative technology and, in the fascinating realm of cosmology, the concepts of slow roll inflation and fast roll inflation represent two distinct scenarios in the early universe, both of which are vital for understanding how our cosmos evolved after the Big Bang. Slow roll inflation, which is often described as a gradual, smooth process, occurs when the inflaton field, a hypothetical field thought to drive inflation, evolves slowly over time. This slow evolution allows the universe to expand exponentially, leading to a uniform and isotropic universe, as fluctuations in density can be stretched and smoothed out. The potential energy associated with the inflaton field is typically very flat, meaning that the field slowly rolls down this potential, resulting in a prolonged inflationary phase. During this stage, quantum fluctuations can generate the seeds for the large-scale structure we observe today, such as galaxies and clusters. On the other hand, fast roll inflation happens when the inflaton field rolls rapidly down its potential, resulting in a quicker inflation. This scenario is characterized by a steeper potential and can lead to a more abrupt change in the energy density of the universe. Although fast roll inflation can still produce some degree of expansion, it often does not allow as much time for the quantum fluctuations to stretch and seed the large-scale structure as effectively as slow roll inflation does. The differences in the dynamics of these two types of inflation also affect the spectrum of primordial fluctuations they produce. Slow roll inflation tends to yield a nearly scale, invariant spectrum of density perturbations, which is consistent with observations from the cosmic microwave background radiation, while fast roll inflation may produce a different spectrum, potentially leading to large variations in structure. Additionally, the duration of the inflationary phase plays a crucial role. Slow roll inflation can last for a sufficiently long time to ensure that the universe becomes homogeneous and isotropic, whereas fast roll inflation, these differences are not just theoretical. They have implications for what we can observe in the universe today, influencing our understanding of cosmic microwave background anisotropies, the distribution of galaxies, and the overall geometry of the cosmos. Thus, exploring these two models not only enhances our comprehension of the early universe, but also helps us piece together the bigger picture of cosmic evolution, shedding light on the fundamental forces and fields that govern the universe's behavior. Inflationary models of the universe propose that, in the moments immediately after the Big Bang, the universe underwent a rapid expansion, much faster than the speed of light, which has profound implications for its large-scale homogeneity. Before inflation, the universe was in a hot, dense state, filled with energy and fluctuations. However, during inflation, this tiny region of space expanded exponentially, smoothing out any irregularities and making the universe appear uniform on large scales. This rapid expansion caused regions that were once close together to be separated by vast distances, creating the large-scale structure we observe today. The homogeneity we see in the cosmic microwave background radiation, which is a remnant of this early universe, is consistent with inflationary theory, as it shows tiny fluctuations that were stretched out over a homogeneous expanse, leading to the even distribution of matter and energy across the universe. Moreover, the inflationary model also provides a mechanism for the generation of the primordial density fluctuations that later grew into galaxies and clusters. During inflation, quantum fluctuations were stretched to macroscopic scales, seeding the universe with tiny variations in density. These fluctuations were crucial because, as the universe continued to expand and cool, regions with slightly higher densities began to gravitationally attract matter, leading to the clumping of matter into the large structures we see today. This process explains why, on very large scales, the universe is remarkably homogeneous, while on smaller scales we see the intricate web of galaxies and clusters. Another important aspect of inflationary models is that they suggest that the observable universe is just a small patch of a much larger, potentially infinite universe. This means that the homogeneity we observe does not necessarily imply that the universe as a whole is uniform everywhere, but rather that, on large enough scales, the variations average out, giving the appearance of uniformity. This phenomenon is supported by observations from telescopes that study the cosmic microwave background, revealing that, despite the local variations we can see in galaxies and clusters, when we look at the universe as a whole, it appears very smooth. In addition, inflationary models help to solve the flatness problem, which is the question of why the universe appears to be so geometrically flat. During inflation, the rapid expansion acted like a cosmic stretching of space-time, leading to a state where the curvature of the universe is very close to flat. This aligns with observations that show the universe's density is very close to the critical density needed for a flat universe. The spectral index, a crucial parameter in inflationary cosmology, plays a significant role in understanding the early moments of the universe, particularly during the rapid expansion. Known as inflation, which occurred just after the Big Bang. This index helps describe the distribution of primordial fluctuations in the cosmic microwave background radiation, which is the afterglow of the Big Bang. Specifically, the spectral index, often denoted as N, characterizes how the amplitude of these fluctuations changes with scale, or in simpler terms, it tells us how the density of the universe's seeds for structure, like galaxies and galaxies, cast different. In inflationary models, a spectral index value of N close to 1 suggests that the fluctuations are almost scale, invariant, meaning that they do not favor any particular size, which aligns well with observations of the cosmic microwave background. When scientists measure the spectral index, they can deduce vital information about the dynamics of inflation, such as how rapidly the universe expanded and the energy scale of inflation itself. A value of N less than 1 indicates a slight tilt towards larger scales, implying that larger fluctuations are more prominent than smaller ones, which influences the formation of structures in the universe. The importance of the spectral index extends beyond just theoretical implications. Observational consequences. As telescopes and satellites, like the Planck satellite, have captured detailed measurements of the cosmic microwave background, researchers have been able to estimate the spectral index with remarkable accuracy, leading to a deeper understanding of the universe's initial conditions and the mechanisms that drove inflation. Furthermore, the spectral index can provide insights into specific models of inflation, such as single-field inflaton models, or more complex multi-field scenarios. Each model predicts a different behavior of the spectral index, thus allowing scientists to test these theories against observational data. The continuing refinement of the spectral index measurements can help distinguish between competing inflationary models, honing in on which best describes our universe's infancy. In summary, the spectral index is not just a number. It is a window into the universe's early history, helping scientists unravel the complexities of inflationary cosmology and providing a foundation for our understanding of the cosmos. The implications of the spectral index resonate through various aspects of astrophysics, influencing theories of structure formation and the evolution of the universe itself. Inflationary models, which describe a rapid expansion of the universe in its earliest moments, have intriguing connections to the concepts of entropy and time, both of which are fundamental to our understanding of the universe. In the context of cosmology, entropy is a measure of disorder, or the number of ways a system can be arranged, and it fundamentally relates to the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. During the inflationary phase, the universe underwent an exponential expansion, stretching out space itself, and this rapid expansion has implications for how we understand entropy in the early universe. At the beginning of inflation, the universe was in a hot, dense state, filled with energy and particles, creating a high degree of order. However, as inflation occurred, the universe expanded dramatically, leading to a rapid decrease in temperature and density, which, interestingly, also affected the distribution of energy and matter. This sudden expansion can be thought of as creating a vast amount of space, which, paradoxically, allowed for a greater degree of disorder, as inflation would have smoothed out any irregularities, leading to a more homogeneous and isotropic universe. In this sense, inflation sets the stage for an increase in entropy as the universe transitions from a highly ordered state to one that is more chaotic and spread out. Furthermore, the concept of time in relation to these inflationary models is equally fascinating. In our everyday experience, time is often perceived as a linear progression from past to future. But in the context of the universe, time can be influenced by events such as inflation. The rapid expansion effectively stretches the fabric of space-time itself, which can alter how we understand the flow of time. For example, during the inflationary period, regions of space that were once close together became vastly separated. And this expansion means that events that might have been simultaneous in a smaller universe could become staggered in a larger, inflating universe. Additionally, the end of inflation marks a pivotal transition in the universe's evolution, leading to the hot Big Bang, where the universe began to cool and structures such as galaxies and stars started to form. This cooling process is essential for the increase of entropy, as energy becomes more dispersed, allowing for the formation of complex structures over time. Relationship between inflation, entropy, and time thus highlights a deeper understanding of cosmic evolution, suggesting that the very fabric of time may have been influenced by the inflationary expansion itself.